Okay, good afternoon and welcome to an encore performance by Professor Dyson. 6 weeks ago, Professor Freeman Dyson gave us a talk here to a standing room audience on the looking forward science and science fiction. This time, we are coming also to a full audience. What it shows is that there is a very, very good match between Professor Dyson's vision of the future and our interest and efforts here at JPL to make it happen. And I'm delighted to see this. As you know, Professor Dyson is a professor of physics at Princeton. He's also a distinguished visiting scientist at JPL. Throughout his career as a teacher, as an author, as a thinker, he has been known for his ability to be a visionary standing on solid grounds. And that is not an easy combination. He has been recognized for his efforts by the many awards and prizes he has received. He is a member of the British Royal Society. He is also a member of the National Academy of Sciences. He has been a professor at half a dozen universities. He has 12 honorary doctorates, and I believe one very honorable PhD in addition to that. Professor Dyson has authored several books. 4 of them have been translated to almost all the well-known languages in the world. He has also received the National Books Critics Award in the United States for his ability to express difficult scientific concepts to people who are involved in science as well as those who are not involved in science. With this, it's my pleasure to welcome Professor Dyson, and let's give him a hand.
So, thank you very much for your kind words, and I'm amazed that so many people come after already being exposed. But anyway, this time I'm not going to be visionary today at all. I wanted to talk about some real stuff, things that are either have been done or are being done right now. And I mean, this was really a talk which was in fact, I gave it at Harvey Mudd College a few months ago, and it was supposed to be a pep talk for physics students, telling them that physics is alive and well, that there are still useful things that physicists can do. And so it wasn't supposed to be visionary. Anyhow, I'd be happy during or after the talk to answer questions or interruptions which can be as visionary as you like. And anyway, so I have a list of topics there. I probably won't get through the list. Doesn't matter, because it's better to talk in detail about a couple of things rather than sketchily about 7. I might just mention I won't talk about number 3, the magnets in human brains, because that's being done by Joe Kirschvink right here at Caltech. And so if you want to hear about that, you ask him to come tell you about it himself. It's a beautiful piece of work, but it's no good getting it secondhand when Joe is right here in town. Well, let me begin with the carbon cycle. So I have here some kind of a device. Yeah, it's supposed to be a signal to tell the projectionist what to do. Oh, here it is, yeah. Good. So there it goes, the mystery of the missing carbon. So I wrote it down here big so that most of you can read it. The point is, the amount of carbon dioxide that human activities are putting into the atmosphere is pretty well known. I mean, the contribution from fossil fuel burning is very well known. It's about 6.5 gigatons of carbon per year. I use the unit of gigatons carbon. You can easily translate that into carbon dioxide if you want. And so that's very well measured. That's 6.5, at least it's plus or minus maybe 1/2. But the other component, which is the result of our mismanagement of the biosphere, that is mostly deforestation and soil erosion. That's not at all so well measured. It's very hard to get accurate figures for that. These numbers are conservative. If you talk to the Sierra Club or the more radical environmentalists, they'll tell you the numbers are really larger than that. Almost certainly they're not much smaller. So I think that the 3 gigatons per year, about 2 gigatons of that is destruction of forests, and about another 1 gigaton erosion, a lot of which is a consequence of destroying forests. When you destroy the forest, of course, the soil goes to hell as well very often. And so anyway, there's a total of at least 9 gigatons per year that human activities put into the atmosphere. But when you measure the actual increase of carbon dioxide in the atmosphere, and that has been done with extraordinary accuracy, it's one of the best measured time series in the whole of planetary science, I suppose, done by one man, Charles Keeling at La Jolla at UCSD, the answer is 3.5. That is, it has been slightly increasing in the last 10 years, but it's about 3.5 gigatons carbon per year that actually stays in the atmosphere. And so you have 5.5 gigatons, which is gone, and that is the mystery. Where is it gone? And so that's what I'm going to talk about for the next 15 or 20 minutes. We're beginning to get a glimmering of where it's going. But I regard it as a scandal, as an absolute disgrace, that this question has not been answered in the last 20 years. There have been, of course, huge amounts of money poured into what's called the greenhouse problem. Department of Energy is spending a huge amount, and other parts of the government too. And they're supposed to understand what's going on to the atmosphere. That is the greenhouse, after all, this carbon dioxide. So why don't we understand what's happening to it? The answer is, I believe, that what is mostly to blame is computers. That if you look at the way the billions are actually being spent, you find by far the lion's share it goes into what's called climate modeling. That is, people sitting in air-conditioned rooms running big programs on computers, figuring out what the atmosphere would be doing if you assume certain things. So you put into the climate models, of course, the amount of carbon dioxide that now is there, and you make estimates as to what it's going to be like in 50 years from now. And then you run the computer models, and that tells you what are the consequences. But what they can't tell you from these computer models is how much carbon dioxide there will be in the atmosphere 50 years from now, because we don't know the mechanism. We don't know why this 9 gigatons a year doesn't actually stay in the atmosphere. So we've not the foggiest notion, really, of how to do a firm prediction for anything beyond the next few years. It's not only the bureaucrats who are to blame for this, it's also the scientists. Scientists have a weakness for air conditioning, and they prefer to sit in air-conditioned computer centers rather than putting on their winter clothes and going out into the mud and the rain. And measuring what's really going on in the world, of course, is a messy business. It's hard work. So I'll tell you about one person who is doing it. And so let's find the button. Here we are. So here is his data. I might just tell you what that means first, and then tell you about the sociology, about who it is. His name is Stephen Wofsy, and he's a professor at Harvard. And he has actually been measuring how the carbon dioxide is going from the atmosphere into a forest. And so here is the actual data. The forest is a little piece of what's called mature deciduous forest in Massachusetts, about 100 miles west of Harvard. And it belongs to Harvard University. And it hasn't been touched much by human hand in the last 50 years. So it's considered more or less mature. It's just a variety of deciduous trees. And it was last harvested, I think, as far as I remember, 70 or 80 years ago. And it's since then more or less just been lying fallow. And so according to the experts, it's not completely a climax forest, but it's fairly close. It's supposed to be at least more or less in equilibrium with the environment. So the general belief among the experts was that it shouldn't be absorbing a great deal of carbon anymore. I mean, you expect forests to absorb carbon fast when they're fresh, when the trees are just sprouting, but once they've got to a certain age, they should be slowing down a bit. So this is a sort of an average deciduous forest from what they call temperate deciduous forest, which means most of the forest in the temperate latitudes is like that. Well, look at the actual results. The solid curves are what's called net ecosystem exchange, which is the actual amount of carbon going down from the atmosphere into the forest. And that's divided into two components, respiration and photosynthesis, which are the dotted line and the semi-dotted line. What you see here is that there's a very strong correlation between the minus numbers mean the carbon is going down into the forest. There's a very strong correlation between the amount of carbon going into the forest and the area of leaves. I mean, most of it goes in the summer months, which is when the trees are covered with leaves, and it stops quite abruptly between September and October when the leaves fall. So it's fairly clear what you're measuring is the actual growth of the forest through the spring and the summer. And in the winter, as you see, it's slightly positive. That's due to the respiration, which is going on all the year round. And whether there are leaves or not, the soil respires. And if you look carefully, you notice that the respiration also is larger in summer, but not by very much. So let's go ahead. So, and that is the cumulative data, which is got over a period of 2 years. That's an old, it comes out of a paper that was published in Science about 2 years ago. He's done 2 more years since then, and the data are very consistent from year to year. See, the bottom curve shows the accumulated deficit of carbon gone down from the atmosphere into the forest. And as you see, it goes down quickly in the summer and then goes up slightly in the winter, then goes down again the next summer. But the overall trend is strongly downhill. That's to say there's much more photosynthesis than there is respiration in this piece of forest. And at the top, you see the same data in differential form week by week. So you see in the summer, the thing comes down sharply, and it's plotted there the same way with both the photosynthesis coming downward and respiration going upward. So then, let me tell you a little bit about Wofsy. He decided, unlike the other climatologists, actually to go out and measure what's going on. And he built a tower 30 meters tall, and at the top of the tower he put a lot of instruments. And so those are the results which he measured. The important thing was that he didn't attempt to measure the trees. A lot of people have tried to do that, and it's extremely hard to get any kind of accurate measurement of the volume of a forest in terms of actual quantity of biomass. It's extremely hard, and of course you have to worry about not only the trees but also the soil, and in practice you just can't do it. So instead of that, he had the idea, why not measure the air directly? And it has actually turned out to be surprisingly accurate, more accurate than I would have imagined. And so he puts these instruments up on the tower above the canopy of the trees, and he measures then furiously all the year round. And well, what are the instruments? First of all, what's called the decisive instrument which makes all this possible is a thing called a sonic anemometer, which he didn't invent, but he put it to very good use. And a sonic anemometer is a wind measuring machine which has an extremely fast response. It consists of a tube in the shape of a C, a metal tube, with open mouths at the two ends, above and below. And through the mouths, you transmit and receive ultrasound waves, actually quite high frequency ultrasound. So you're emitting ultrasound waves from the upper mouth of the sea and receiving it at the bottom mouth, and at the same time transmitting from the bottom and receiving at the top. And you measure phase differences. And of course, the sound that's going upward will go slightly faster if the air is also moving upward, and the sound that's coming down will go a little bit slower. So you'll measure a phase difference between the upgoing and downgoing waves, which then tells you the motion of the air. And all the other environmental effects, things like temperature and humidity and pressure and all the other things that might influence sound speed, cancel out in the difference. So the only thing that's different between upgoing and downgoing is the speed of the air. It's just the convection of the sound waves. So you actually can measure the speed very promptly and very accurately. And what is more, you do it 4 times a second. So he's measuring all the year round, day and night, and recording the information 4 times a second. Well, he has another instrument also on top of the tower, which is an infrared spectrometer, which measures carbon dioxide. It's simply an absorption cell, which you can actually measure very fast the absorption in one of the strong lines of carbon dioxide. And that also can be done very promptly. And so you get a good measurement of carbon dioxide abundance as a function of time, 4 times a second. And then you have a lot of other instruments. He measures also just for their, which they're also contributing to the greenhouse, methane and carbon monoxide and ammonia and, of course, water vapor, various other gases in the air, and all of the usual meteorological variables. And then he takes all these readings down the tower to a computer at the bottom, and he has a powerful, not very big, but sufficiently powerful data processing system. So all this data is recorded promptly, analyzed, and it's far more 100% available than most meteorological data. The big difference between these instruments and the sort of old-fashioned meteorological instruments is that these are very, very rugged, that especially this sonic anemometer functions even when it's raining or snowing or thundering or hurricane blowing and or all the other things that happen in Massachusetts at various times of the year. Most instruments collapse in foul weather, but these don't. The only thing that actually defeated him up to now is direct lightning strikes on the tower. Those do cause a spot of bother, and he actually lost a few days of data as a result of direct lightning strikes. And he's trying to figure out how to deal with that. But, I mean, you could, of course, deal with it after a fashion just by having several towers and relying on not being struck simultaneously. But anyhow, that's still a problem. But still, when you put this together, let me then say what these units are. I find it convenient to use this WAFC unit, which is 1 metric ton of carbon per hectare per year, which is, if you look at what it actually means in terms of biomass, you see it's 0.5 millimeter of biomass per year. And that explains why it's so almost impossible to measure it directly. How can you possibly tell whether a tree has got 0.5 millimeter bigger than it was the year before? And so he's able to deal with that by measuring this air. So I now this is some more stuff which you can read for yourselves. It's convenient to use as a unit of area the gigahectare, which is so that's 10 to the 9 hectares, which is 10 to the 7 square kilometers. That's a convenient unit because it converts local measurements to global measurements automatically. So 1 WAFC unit, it's one ton of carbon per hectare per year. It's also 1 gigaton of carbon per gigahectare per year. And as you see, the gigahectare is a convenient unit. The total land area of the planet is 10 gigahectares. The United States is 0.7. And the total area of temperate deciduous forest is 1.3. So they're convenient small numbers measured in gigahectares. So then, if you look at the actual global numbers, you see that they're remarkably small, that the amount of fossil fuel burning divided by the total land area of the Earth, that's 0.6 in these units. If you take the actual increase of carbon dioxide in the atmosphere divided by the total land area, it's 0.35. So those are small numbers, considerably smaller than 1. And if you take the total CO2 in the atmosphere, of course it's a remarkably small concentration, divide that by total land area, it's only 70 WAFC unit years. So it means if you're absorbing at the rate of, say, 3 WAFC units per year, I mean, not that's already per year, 3 WAFC units, it would only take you 20 years or so to use up all the carbon dioxide there is. That shows how small the reservoir of carbon in the atmosphere really is compared with other things. So here are his results. This is now the bottom line, that he actually measures directly the net downward flux. So that's directly measured. That's 3.7 plus or minus 0.7. And that 0.7 uncertainty is very generous. I mean, it's hard because these are all systematic errors rather than random errors. So you can't say it's 3 sigma, but it's something like that. I mean, it's an outside limit of the error. The error is actually mostly due to conditions at night when it's hard to make the measurements because the air gets stratified and stagnant at night and it's not convecting. And so there you have a somewhat a real uncertainty, but these stagnant conditions are not present very much of the time, and they happen more in winter than in summer. So it's unlikely that you make a very big mistake just by forgetting about those times. So that's where that point plus or minus 0.7 mostly comes from. Well, you see the actual measured downward flux is this 3.7. And that's approximately 5 times what the experts had predicted. The general belief among the experts. I spoke with a number of experts, and I asked them, is it possible that the carbon dioxide is going into the forests? And they said, no, it's certainly not. I mean, you know, the forest couldn't possibly be absorbing anything like this 5 gigatons that's missing. And they say at most 1 WAFC unit was their general estimate. Well, it turns out to be 3.7. So much for the experts. And well, these other numbers are more or less taken just by adding. You can also measure the flow of carbon below the canopy, and so you get then more or less the soil respiration by itself. And so that 7.4 is more or less a measured number. And the 11.1 is just got by adding the respiration to the net flux. So it's not directly measured. I mean, this is a good thing because the big numbers have larger uncertainties if you try to measure them directly. So the important one is this net flux downward, and that is measured directly. Well, where does this measurement come from? Here is the only equation I'm going to show you in this whole talk. Those of you who don't like equations, you don't have to suffer much. So F is the flux you're measuring. It's simply the correlation between the upward flow of air. The air is constantly turbulent, at least most of the time, above the forest. It's just convective eddies, mostly a few meters in size. And there's also just ordinary winds. It's a mixture of all kinds of meteorology, but on a local scale. And so you're simply measuring locally the upward velocity of the air, multiplied by the local concentration of carbon dioxide, and integrate over time. That's all you're doing, just taking directly the correlation between upward speed and concentration of carbon. And of course, the idea is that every time the air is moving upwards, it takes up a certain amount of carbon, and every time it's moving downwards, it takes down a certain amount of carbon. And if there's more carbon in the air when it's going down, then the net flux will be down. That's all it is. And now you might think this is a tremendously noisy kind of a measurement because it's all fluctuating all the time. You have no control over the meteorology. But the amazing thing is that in fact it's almost all signal and very little noise, because it happens that these quantities are almost 100% correlated. If you actually measure the correlation over a minute or two, you find they're highly correlated, something like 80 or 90%. So it means that on that kind of a time scale of the order of seconds and minutes, in fact, there's essentially a steady flux. When the air is jittering up and down, but every time it goes up, it's taking less carbon up. Every time it's going down, it's taking more carbon down. So in fact, this integral is mostly just all the same sign. And it has very little, actually very little cancellation at all. The flux is almost always, even on a short time scale, the flux is almost always going down, except in the winter when it's going up. And so it turns out to be surprisingly reproducible and surprisingly accurate. So then this is sort of the moral of the story, that these three innovations are what makes a revolution in the art of what you might call the monitoring of the biosphere. First of all, these are accurate and rugged instruments. And then the year-round continuous data measured at 4 hertz and a computing power adequate to collect and process the data. And that really does make a revolution. Now, why am I so excited about this? Why should I care about the little piece of forest in Massachusetts? And so that's, I've already told you, I don't need that. Oh no, this is the next one. So forget it. I'll just tell you a few more things before I get on to proteins. The reason why this is important is that if you take this 3.7 WFC unit that is actually measured in Massachusetts, and you multiply that by the total area of deciduous temperate forests, which is 1.3 gigahectare, then the answer is 5.0 gigatons of carbon, which is rather a remarkable coincidence. It happens to be just exactly equal to the missing carbon. Of course, that doesn't prove that the entire temperate deciduous forest is actually absorbing carbon at the same rate as this piece in Massachusetts. That remains to be tested. But it could be so, and that's why it's exciting. So obviously the thing to do is multiply WFC's effort by a factor of 100 or so. I mean, it's a trivial amount of money compared with what we're spending on climate models, let alone the other things that the Department of Energy does. And this entire research of WFC for 3 years cost $500,000 and got these very definite positive results. So if one merely just multiplied that effort by a factor of 100, it would cost you 50 million. And you could do it in all kinds of places, in all kinds of parts of the world, taking samples. I mean, it doesn't have to be all temperate deciduous forest. You'd like to do it in the Amazon, which WFC is already doing. You'd like to do it in the coniferous forest in the north, which WFC is already doing. And you'd like to do it in farmland, in wetland, in all kinds of places, to find out what we're actually doing to the biosphere. And there's no reason why we shouldn't be doing that. The money is certainly could be available. It's more difficult to find enough people willing to go out and do it. And that it's not so easy to multiply by 100 in a short time. But at least we could be multiplying it by 10. So that's what I'm preaching, that this could be a completely new outlook on the greenhouse problem, that instead of just messing up the biosphere in the dark and blindly, we could actually be messing up the biosphere with our eyes open and actually knowing what the effects are. I mean, it's, for example, if you just take the case of simple things like to irrigate or not to irrigate, or to farm without plowing or to farm with plowing. It's generally believed, of course, that if you farm without plowing and plow in the, I mean, don't plow, but just allow the crop residues to stay in the ground, that's good for the biosphere, that it's likely then to increase the organic compound of the ground and at least reduce soil erosion. But nobody's proved that, and this way you could actually be sure, you could actually measure locally the effects of all kinds of different sorts of farming, different kinds of crops in different places. And of course, one thing you can also do, which I've been advocating for many years, is actually planting trees or watering forests that already exist, or moving water to forests or moving forests to water, whichever happens to be more convenient and cheaper. And it's fairly obvious that this is going to help the greenhouse problem, but we don't know for sure. And now this way you could measure, you could actually be sure what the effects are before you go into some huge project. You could measure it locally. So I think this might be a very important part of handling what I call sort of global land management, which I consider is what you have to do in order to deal with the greenhouse. I think that the real cure for the greenhouse problem is not restrictions on fossil fuel burning, but it's land management for the whole biosphere, which is in many ways a much more potent technique and likely to be beneficial for other reasons besides the greenhouse. Well, that's enough. I've already taken half the time. I must at least... No, I don't want a new one. I'll keep this one. That's this one we haven't talked about yet. This is protein structure. Now, this is a complete change of topic. I'm not talking about science, not about the biosphere. This is actually important for medicine. The point is that finding the structure of proteins is extraordinarily labor-intensive, tedious work. And we have, of course, found out how to do it about 50 years ago. The first two proteins to be structure analyzed by X-ray crystallography were myoglobin and hemoglobin. I remember that very vividly because I'm that old. And it was a great triumph. Perutz and Kendrew both got Nobel Prizes for this work. And they discovered how to sequence proteins. I mean, not sequence, that's different. To structurally analyze proteins, to find the precise structure. Well, 50 years later, you count up the total number of proteins whose structure has actually been measured. The answer is 519. That was in October last year. It's a pitifully small number. I mean, you know, it's 10 per year. So if you think about just for medical purposes alone, you'd like at least to know the structure of all the proteins in a human being, which is about 100,000. Well, at this rate, it'll take 10,000 years. Actually, from a medical point of view, because you'd like to know a lot of other proteins besides, you'd like to know the structure of proteins of the AIDS virus, of all kinds of bad disease, bacteria and such, and not to mention the beneficial creatures. So you should probably multiply that 100,000 by at least 10 for the rest of the biosphere. We're not the only creatures you'd like to analyze. So anyway, the medical importance of this, I would say, is at least as great as the importance of sequencing DNA. But for some reason, DNA has got all the pizzazz and proteins have not. And I think that it's time that changed. Because the reason why DNA sequencing has got so much more publicity is because it's going much better. That, in fact, sequencing DNA turns out to be easier than finding the structure of proteins, just for technical reasons. But that's no reason for neglecting the proteins. Anyhow, so John Seidels, who is the hero of this second incident, is a physicist. He's actually a real card-carrying physicist with a PhD in theoretical physics, but he works in a medical school. And so he sees urgencies which most of us don't. He's actually in the orthopedics department at the University of Washington Medical School. And he got the idea of, see how this goes, what's called oscillator-coupled MRI. So the idea is to actually look at proteins one at a time, literally one molecule at a time. why is that so important? Because the real difficulty with sequencing, I mean, I shouldn't say sequencing, the real difficulty with finding structure of proteins by the classic method of Perutz and Kendrew is it requires good crystals. And so you have to, if you use X-ray crystallography, you have to start out with a crystal, and it's hard to crystallize proteins. Many of them don't crystallize at all. And before you even try to crystallize them, you have to purify them, and that's extremely difficult. And the reason myoglobin and hemoglobin were done first is because they're very abundant. Each of us have lots of myoglobin and lots of hemoglobin. So there's no problem about getting enough of the stuff. And it happens they also make crystals. But the average protein is only present as a trace in human cells. And it's a major undertaking to get to purify enough, even to begin the structural analysis. So if you want to do this job, Seidels decided what you have to do is look at proteins by one molecule at a time. That's to say, look at them directly in 3 dimensions in real space, not in Fourier space. And so he had the idea of combining 2 technologies, which both are flourishing technologies which have been doing well. One is MRI, that's magnetic resonance imaging, which is, of course, a wonderful tool which is used all the time in medicine. And it has marvelous penetration. That is, it gets inside you so you can actually see tumors growing in your brains. And so it saves enormous numbers of lives. And it's also useful for orthopedics. And, but its resolution is poor. That is, in the standard version, the resolution of the standard MRI apparatus is about 1 millimeter, which is very good if you're looking for cancer, but not good if you're looking at inside individual cells. Well, there are, of course, a lot of quite serious efforts going forward to make MRI microscopes, to make MRI with much higher resolution. And this is, so it's not true that it necessarily is limited to 1 millimeter, but it's not good enough. Even the good MRI, with high resolution MRI, is not good enough for looking inside molecules. On the other hand, there's a different gadget called the atomic force microscope, which is also very useful, which is mostly used by surface chemists. It's for studying hard surfaces, and it has fantastically good resolution. It's actually just a very sharp point, a tiny little very sharp point, which is attached to a very weak spring, just a whisker, and the weak spring carries on it a tiny little mirror, and a laser is transmitting light at the mirror, and the reflected light is interfered with the transmitted light. So you can measure by the fringe shift, the phase shift of the laser, you can actually measure displacements of this little whisker with extraordinary accuracy. So you get, as you scrape the point over the surface that you're observing, and as the point jerks up and down, you can actually see the individual atoms in the surface. The resolution is about 1/10 of a single atom. So the resolution is fantastically good, but of course no penetration at all. You can't see one atom below the surface. So it's wonderful for surface physics, but no good for looking inside a protein. So anyway, the combination of these 2 is a thing called magnetic resonance force microscope, which is the thing that Seidels invented. And Seidels actually invented it. He called it oscillator-coupled MRI, but that name hasn't stuck. I think this was about 2 years ago. It's all quite recent. I think the official name is now MRFM, which includes various other things which are not precisely oscillator-coupled MRI. So the 2 of the experimental groups that are working on this are Dan Rugar at IBM Almadane and Michael Raux here at Caltech. And both of them are going ahead very fast. So some experiments have been done which demonstrates the thing works in principle. So that's what it looks like, more or less. This is one of Seidels' pictures. It's, of course, very schematic. It doesn't really look like that. This thing that looks like a tuning fork is your mechanical oscillator. And instead of having a sharp point and scraping it on the surface as you do in the force microscope. Instead, you have this little speck of ferromagnet, which he calls the magnetic source, which is just a little speck of iron, which produces locally a very strong inhomogeneous magnetic field. And that's supposed to interact then with an atom or some other little tiny magnet in the surface that you're observing. And it works like a magnetic resonance instrument in that this atom in the surface resonates in a strong magnetic field. It has a magnetic resonance at a well-defined frequency, which depends on the local magnetic field. And if it's at exactly the same frequency as the mechanical resonance of the oscillator, the two are coupled together. The magnetic resonance of the atom actually are coupled physically. There's a force between the atom in the substrate and the mechanical oscillator. So when you switch on a oscillating magnetic field in resonance with the atom, you actually can observe the whisker starting to vibrate. The two are coupled together because the magnetic field is very inhomogeneous, so that it actually produces, when the magnetic source moves, it actually produces a force. Or even if it doesn't move, it produces a force. So anyway, there is a mechanical coupling. So there's a picture of how you do this, sort of use this as a scanning device. That you have your surface, and the atoms are underneath the surface, the ones you're looking at. And this little sphere is supposed to be the speck of iron. So the field in the neighborhood of the iron is varying strongly with depth, so that the resonant frequency is varying with depth, so that the atoms which are in resonance have to be at a certain definite depth, or at least they have to be on a certain surface. So then you scan this two-dimensional surface by moving the tip around, and so in that way you can localize the magnet that's resonating in 3 dimensions, and so in principle you can scan and get a complete picture of the space distribution of the magnetization. Well, that's the principle, of course. In the real world, it's a lot more complicated than that. So there's a circuit diagram. Well, I don't want, but I think I'll skip that. So here is the first experiment, which was actually done not with a single atom, of course. This was a little speck of paramagnetic salt. So what you're observing is actually electron spin resonance resonating with this mechanical whisker. But anyway, the nice thing is that the experiment worked, at least demonstrating that the idea isn't totally crazy. And here's just another run with 2 little specks, showing you can actually resolve 2 specks. You see that the experimental result follows the theory very exactly. And so you can actually, the resolution here is about 10 microns, which of course is not at all the size of a molecule. But so anyway, that's as far as it's got, more or less, except I think Rugar has measured he did a nuclear version of this experiment, so he was observing a nuclear resonance, but in a macroscopic sample. Well, how far do you have to extrapolate this to reach molecules? Well, this is the John Seidel's sort of grand strategic plan, and so you're going. What you're measuring is the force of which is coupling the magnet to the mechanical oscillator. So you start out at the top with 10 to minus 14 newtons, and that's the first experiment that I showed you. And then the next experiment was nuclear magnetic resonance, which was 10 to minus 15, and then you go on down, and so first you have to make thinner and thinner whiskers to improve the sensitivity, and then finally the big step is cooling to 4.5 Kelvin. The theory says that the sensitivity of the instrument is roughly proportional to temperature. It's essentially thermal noise that you're dealing with. So if you cool down from room temperature to 4 degrees Kelvin, that gives you something like a factor of 100. And so that will get you down to something like 10 to minus 18 newtons. And then you have to increase the Q of the oscillator and do various other tricks. And finally, around 10 to the 19 newtons or so, you get to the point where you're doing single protons. Of course, that's not good for human subjects to be at 4 degrees Kelvin, but fortunately, this kind of experiment is being done on molecules. Seidels is interested in both aspects. If you go down as far as you can go at human body temperature, you won't be able to see molecules, but you might be able to do very good imaging of cells and structures in cells. So the sort of the resolution you can get at room temperature should be of the order of microns, or even a tenth of microns, which will be very good for visualizing cells. And so he's interested in that for medical purposes. But the more important is the chemical regime, which is down at helium temperatures where you might expect to see the individual atoms. So that's not intended. There should be. Yeah, this is another thing which I won't have time to talk about. That's Jerry O'Neill's VSE trains, which is one of my favorite projects. Unfortunately, he died last year, and the thing is left unfinished. But we have to keep on going. Or didn't I give you any more? Or maybe that doesn't matter. Anyway, I'm pretty well. It was only words anyway. But the let me just pick up the thread. No, I think it's because when I've given this talk before, I always had the few graphs in my hands and could shuffle them around. But I think maybe I'll just finish off with a few. The hour is almost finished, and this is tempting to say a few words about VSE. VSE stands for velocity, silence, efficiency. And so this is Jared O'Neill's idea for a fast train. It's actually not a train at all. It's a little compartment. And it runs like a telephone exchange, essentially. I mean, it's a telephone network. So you jump into your little compartment, and there's supposed to be a tunnel network. And these are standard gas line tunnels. They're very cheap. I mean, the whole idea is to use off-the-shelf hardware, nothing fancy. And the sophisticated part is the switching network. It's like a telephone system in that respect. So you get into your little compartment, and there's a station underneath every shopping mall. So it completely avoids the problem of airports and traffic congestion and so forth. So you just go to the nearest shopping mall and leave your car in the lot, and then get into your little compartment and punch in your destination. And every trip is non-stop, so there's you never change. You just get in at wherever you get in and get out at the destination. And the problem is just how do you do the switching so that so you don't have two people talking at once. And I mean, the telephone network somehow solved that problem, and at least it's not very often that two conversations get mixed up. And Jerry O'Neill believes he can do it with human beings too, and I think there's a chance he could. I mean, the whole point is that he's essentially arguing that if you want to do fast trains, then the conventional magnetic levitation is not the way to go. That is, it's just not radical enough. It doesn't give you enough improvement over either automobiles or airplanes to be a winner. And I think he's right, but it's possible it might work in Japan, since the Japanese, of course, have a love of railroads, and perhaps even the Europeans, but it's not clear that it will work even there. There's a little bit of a problem also with the acceptability of maglev as far as the health effects of magnetic fields are concerned. That's also a problem, which O'Neill's system avoids that too. The passengers don't see any magnetic fields. But so what he's saying is that what you ought to do if you want fast trains is to have a vacuum pipe, first of all, and just go fast, really fast. And so you have actually not a very high vacuum. You want to have enough air in the pipe to conduct away the waste heat, which, and of course, low density air has a very good conductivity and very little drag. So you actually can do quite well with a small fraction of an atmosphere of air. And then, so you zoom with an acceleration of something like 1/10 of a g, a modest acceleration, which is not as high as a conventional subway train. You can go really fast. I mean, the idea is that from here to Boston, you go about, the trip takes 55 minutes or something of that kind. So it really is faster than going by plane, apart from and avoiding all the hassle of getting to the airport, which is much worse than the flight itself. Okay, so I think that's enough. I'll then, those of you who want to leave can leave, and the rest of us can stay and have questions. Thank you.
Okay, start here.
I have a question about your first talk. It was very interesting. I mean, the first subject today, not the first talk you've made. Considering the balance that occurs today with the amount of carbon dioxide that's being absorbed by the forest, there's less forest than there was 300 years ago, and there's more carbon dioxide generating sources than there were 300 years ago. What in the world was the balance like then? Has that changed significantly since then?
We don't know, but probably there was about as much forest in those days as there is now. It's, but we really don't know. I mean,
my presumption was that, according to Sierra Club, we've lost a lot of forest since then. So my presumption was there was a lot less.
Yeah, it's hard to tell. I mean, I know that they did a study in Venezuela. This was done by the Sierra Club, by the way, and they found that actually there's more forest now than there was 100 years ago. But that's just that's sort of anecdotal. But by and large, we don't know. I mean, we know, of course, in the eastern United States, there's been a lot of regrowth, because most of the area around New Jersey, where I live, was growing hay for horses. So there was very little forest 100 years ago. And now, of course, there's quite a lot. But so you have to look in detail. It's very hard to tell without actually going there and finding out what happened on the ground.
What's a star car?
Well, that was another interesting project. That's Stephen Crow at the University of Arizona. And it's a hybrid automobile airplane. Interesting. It's again, I mean, the interesting part of it is not the vehicle itself, but the system. It's it's essentially it's a creative use of GPS. So that the thing is supposed to be sort of, you have a car which has a detachable chassis, and so you leave the body behind and you go into a sort of rent-a-car place, and they take off the chassis and put on the wings, and then you fly off, but you don't have to be able to pilot the thing yourself. In fact, it's all autopilot with very precise GPS control. And he actually, the one part of it he has demonstrated is the precision of the GPS control, which is good to about a foot, using differential GPS. And so then you punch in your destination. He's actually planning to go commercial with this. I don't know whether it'll actually work, but the idea is a good place to start would be the run from Phoenix to Tucson, which it's a nice piece of country where there's not too many people living underneath, and but it's still too far for comfortable driving. And so anyway, so you have this sort of rent-a-car service. You fly with this wings attached to your car body, and then at the destination you put on a fresh chassis and drive off to wherever you want to go. And I hope it'll work. I think it's a kind of system that's clever from a sociological point of view, and in fact the engineering of it is not very difficult. You don't need high performance airplane for this. It's not supposed to be a high performance plane. And the fuel economy is excellent. I mean, it beats the automobile quite comfortably, and it beats the commercial airliners also.
Any questions?
Yes.
Okay, that's about star cars. How about the last one, I think, oxygen depletion?
That's an interesting one, and in fact, I could talk for half an hour about that. The question might have arisen. I mean, for some reason, everybody was excited about carbon dioxide, so we're producing a lot of carbon dioxide and pumping it into the atmosphere. But at the same time, of course, we're using up the oxygen. And you might have imagined that people would have been interested in that, but there's been absolutely no public discussion of that as far as I know. But I think it would be important to measure, and I tried to get people to do it, and it's very hard. Actually, the son of Charles Keeling is Ralph Keeling. He is trying to do it. Charles Keeling is the one who measured the carbon dioxide and has done such a marvelous job with it. So his son is thinking of devoting his life to the oxygen. It's tough, but I think it's quite feasible. And there's another competitor called Keith Bonin, who is a young man who is now at Wake Forest University in North Carolina. He was an assistant professor at Princeton, but when he announced that he wanted to do this oxygen measurement, the university immediately denied him tenure. It's unfashionable, it's not real physics. And so anyway, that's the way Princeton is, and I'm afraid a lot of other physics departments are like that. So he was kicked out, but he's continuing at Wake Forest and seems to be doing all right. But it's not clear whether it'll actually be feasible in the sense of without a much larger effort. I mean, obviously, in principle, it could be done. The problem with the oxygen is just that there's so much of it. So although the absolute amounts are large, it's still in the order of parts per million. I mean, what you expect if you're actually using up the oxygen so at the same rate that you're burning coal and oil, it's of the order of 10 parts per million per year. But that isn't impossible these days. I mean, to measure 10 parts per million shouldn't be all that hard. In principle, what makes it hard, of course, is that oxygen is very reactive. It's in many ways nasty stuff to deal with if you want to deal with great precision. And so it's hard to find bottles to put it in. It's hard to find old samples. It would be very interesting to look at some old air and see whether the oxygen is much richer 100 years ago than it was now. But any possible, unless you make a very, very careful bottle with very, very careful washing out with strong acids and all the other things you have to do, the walls will absorb oxygen, and so it's very hard to preserve samples for long periods of time. So anyway, I wish these two people well, and I hope very much we'll have the answer. It's important also for understanding what's going on with the carbon, because if you have, for example, if the carbon is not going into the trees, it must presumably be going into the ocean. And if it's going into the ocean, it will be messing up the oxygen in the ocean, but it won't be messing up the oxygen in the air. So you could tell by measuring the oxygen where the carbon is going. So there are all sorts of reasons for doing the measurement, but it was never got any support from the Department of Energy. And even now, it depends really just on the dedication of two people. Yes?
Net downward airflux over the temperate forest, then presumably there's a net upward airflux elsewhere to maintain fairly constant pressure. Or is that?
No, it's only the.
Your formula shows you take the carbon dioxide concentration and multiply times the vertical wind velocity of the intervals of that. You could do the same thing with nitrogen or oxygen and say, well, all this oxygen is going into the forest, or all this nitrogen is going into the forest.
Well, in fact, the oxygen is presumably going upwards. But the point is that these are presumably counterbalanced over the long run. If you wait for 10,000 years, it'll come into balance with the oceans. The oceans are constantly exchanging gas with the atmosphere, probably on a larger scale than this. But they're more or less saturated. The surface layers of the ocean are saturated with both oxygen and carbon dioxide. And then there's a complicated chemistry involving carbonates, which buffer the carbon dioxide. So in the short run, the thing doesn't have to be in balance at all. And presumably, in year to year, there may not be any kind of a balance between what comes up and what goes down. Yes?
I think it'd be a good idea to put a WAFC device on polar cap of Mars.
That would be interesting. I would wait until we've settled the place.
May I ask you
yes.
a question? I thought about it while I was sitting here. You gave us two examples, okay, where three technologies available were put together to provide something unique.
Yes.
For the second one, you had two of them. If you look at our space program here, what would you suggest as one, two, or three technologies which could be fused together, okay, to give us something really unique? Yes.
Yeah, well, it's hard to have brilliant ideas just just on demand, but
for you it's easy.
No. I mean, of course, the things I've always been plugging for our space program are, first of all, solar electric propulsion, which I'm very fond of, and I'm very happy to see that it's now finally getting some solid support. And another thing I love is solar sails, which doesn't necessarily combine well. I mean, probably one or the other is enough, because they're more or less doing the same thing. They're giving you low thrust for long periods of time. Yeah, and then of course there's the whole game of miniaturization, which goes very well, because I mean the reason why both those technologies were not used for propulsion was primarily because people were thinking in terms of huge payloads. And on a scale of a couple of ton payload, of course, solar sail gets awfully cumbersome. It means it has to be of the order of square kilometers, and it's not a very attractive idea to get to be the first astronaut who is tangled up in a solar sail. And so I think that's probably the reason why the solar electric also has been delayed so long, is because people weren't thinking about small payloads. And solar electric is one of these things that just loves small payloads, because you have, essentially, the problem is that it's a demanding technology. Things have got to last for long periods of time and not burn out, and all those things are much easier to test and to develop on a small scale. In fact, I think it should be even on an even smaller scale than it is. So I look forward to the 1 kilogram spacecraft with a solar electric propulsion unit, which has weighs a few grams and has a thrust of micronewtons rather than newtons. So I hope those things will come, and I think those will work extremely well together. That's all I can think of just for the moment.
Well, that was an easy question. Do you have a hard one?
Yes.
What's your opinion about the feasibility of nanotechnology for building machines on the scale of molecules?
Well, I think it's a question what you call nanotechnology. I mean, the sort of customary definition is that it's something different from molecular biology, and that it's so. It's the idea was to. Well, I think the fact is that molecular biology has become so powerful that it's sort of overtaken the mechanical nanotechnology, or it soon will. I think. 10 years ago, it wasn't so clear that when Eric Drexler started the nanotechnology campaign, and I think it is a good idea, but it looks to me as though the molecular biology is going ahead so fast that in the end it'll probably turn out that will be the way to do nanotechnology rather than to do it mechanically. But still, it's worth having both anyway, because there'll always be things you can do better a different way. But if I wanted to develop nanotechnology now, I would say go the biochemical route. Are you doing it yourself?
Okay.
Yes.
Final question. Go ahead.
You're talking about combining technologies, and they're having proposed satellites for essentially a cellular world where anybody could call up on their cellular phone. Well, even better, something like WAPC's instruments. Very simple arrays being plunked down by mujiks or campesinos or even suburban Californians, being very optimistic. And it would be very simple for people to run. These things would, on a weekly basis, might call in and give a cellular data dump to where you'd have not hundreds but thousands of data points throughout the globe for checking carbon flux or any other flux you wanted to measure.
Yes, I think that makes a lot of sense. It's a question of economics. As long as you have less than 100, it's probably just as well to have people to take care of them. And when you get to the point where you run out of people, which you probably will, who will have the motivation or the training to do this, then you'd start automating. And certainly in the long run, if it becomes absolutely routine, of course, automation is the way to do it.
All right. Thank you very, very much.